In this lecture, we're going to begin to talk about object-oriented programming, which is actually a rather broad topic. If you take a computer science major at a four-year university, you're probably going to spend 2 semesters in your undergrad at least, and maybe 2 more when you get to graduate school if you choose to go that path. So it is a large topic, certainly not one we can cover fully in one lecture, but we do need to learn about it because we use object-oriented programming by design in C#. There is no other way to write code other than object-oriented code. So it pays to really know the basics, and that's what we're going to cover in this lecture. So what is object-oriented programming? Before we can talk about that, we really need to talk about what the 2 big paradigms are. There are more paradigms, but these are the 2 big ones. So the 2 big ones are procedural programming, which is what we had in, say, the mid-'80s and before that, and we still have it today. It's actually enjoying sort of a resurgence. People are starting to write more software using procedural paradigms and procedural languages. And there are even a lot of programming languages that allow you to mix the paradigms. You can choose which one you'd like to use. PHP, Python, there are a number of very popular languages that let you mix them. So let's talk about what the 2 paradigms are. Procedural programming is generally just using global variables and functions to create a program. What a global variable is, if you just imagine what you think a global variable is, just think of the word global, think of the word variable. We've talked about what variables are in another language, so you know what I'm talking about there. You realize that global probably means that it's available everywhere, and if you thought that, then you would be absolutely correct. When a programmer creates a global variable, they're basically saying that that variable is available at all times and to all functions within a program. They can be changed inside of functions, and when we do that, this is called programming with side effects. We're not manipulating a variable inside of a function, we're manipulating a variable outside of a function, and so that's why it's called a side effect. Functions do all of the work in the program. So there's a main method, or a main function that is the entry point for the whole program. And then after that, that main function calls all the other functions, and that's what drives the program and changes the variables and changes the state of the program as it executes. And so that's how we wrote software basically from the 40s until the mid-'80s, when we started using a new paradigm, which is called object-oriented programming. So I'll give you a quick example. This is a Python example. I chose Python because Python is widely regarded as an easy language to read and an easy language to understand. We are not covering Python in our Unity C# course. But since we haven't learned any code yet, assuming this is your first course in programming, I might as well throw something at you that's easy to read instead of diving into something else. And as I mentioned, we're learning C# for Unity. You can only write object-oriented code in C#. You can't write procedural, so there's no way for me to give you a C# example. So I figured this was the next best thing. So what you're seeing here is at the top at line 1, we're seeing a global variable. You can see that it's there at the top, and since it's out there by itself, outside of any of the functions, that's what makes it a global variable. And then you'll see a couple of functions in here. In Python, you declare a function with the keyword def. So on line 4 and line 10, I've created a function on each of those lines. One's called main on line 10, and that is the main entry point for the program. And then the other function that I have is on line 4. It's called change my integer. So I've got my integer at the top, a function called change my integer, and main, which is the entry point. And main just calls change my integer twice, passing in an argument 18 and 21 respectively on lines 11 and 12. And so all that's really doing is it's passing a value into that function on line 4, change my integer. And I've created an argument called toWhat, which is a type integer. That's what that :int means. And in Python, it doesn't assume that if you use a variable name in a function that matches the name of an otherwise global variable, that's the one that you mean. So you actually have to tell it. This is unique to Python. Most languages wouldn't require you to do this, but in Python you have to tell it, hey, I'm talking about that global my integer variable up there at line 1, so don't create a local version of it. I want you to use the global one. So really, that just kind of drives the point home that we're dealing with a global variable. And then all I'm doing on line 6 is I'm taking whatever is passed in and I'm setting the value of my integer to whatever was passed in. The variable name, or the argument name in this case, is to what. And then I'm printing a message to the screen that says, my integer has been changed, it is now, and then I'm concatenating a string version of that number so that we can see on the screen that this works. So that is a procedural program. And if you want to know what lines 14 and 15 are, those are really specific to Python scripts. And that just says, hey, if this is running from the command line, all we need to do is just run the main method. That's just pointing back to the entry point of this particular program. So this is a quick example of a Python script written entirely in procedural code. And again, this sort of makes the point where everything is done with functions and global variables, and all of the data are manipulated inside of the functions, and the state of the program is maintained by these global variables. All right, so let's talk about the other paradigm. I'm tempted to call it the opposite. It's not really the opposite. OOP and procedural programming are not opposites because there's not really any sort of polar difference between them. So I refer to it as the other paradigm, and there are other paradigms besides object-oriented programming and procedural programming, but these are the ones that most people use and most languages, at least general-purpose languages, are using today. And then sort of the newer variants are just going to be variations on procedural and object-oriented programming. So object-oriented programming, we sometimes abbreviate this. We often abbreviate this as OOP. And so if you see anything that says OOP, we're talking about object-oriented programming. In OOP, in this paradigm, instead of breaking things down into functions and then manipulating these global variables, generally what we do is we model real-world things. And this is where it gets a little sticky as a lecturer talking about object-oriented programming, because the word object means something in English, and it also means something in programmerese, if you want to call it that for lack of better term. A programmer, if you say object to a programmer, he thinks something. If you say object to anyone on the street, they're going to think something else. And so those two words are hard because, well, they're the same word, but the two different versions of that word are difficult because it's really easy to describe an object, programmer object, in terms of a real-world object. And that really is the whole point of object-oriented programming, is you need a way to model real-world objects in code. And that's really how it got its name, object-oriented programming. So I'm probably going to stumble over those words a little bit trying to get them straight so that I don't use them interchangeably. And so you're going to hear me describe real-world things. So things, think of a noun, a person, place, or thing, can be described, and there are ways that you would go about describing it. So as we go about describing it, I'm going to draw a little diagram for you, and there is a special diagramming method that's used by programmers, and it's very easy to understand. And so I'm not going to spend a whole lot of time covering it right off the bat because I don't want you to get bogged down with diagramming rules. So let's describe a bicycle. That's a thing, and it's something that's in the real world, and it's something we all have experience with, so I think we can all do a good job of attempting to describe it. So let's talk about what traits a bicycle has. So let's think about the words you would use to describe a bicycle, and then let's group them into traits. So this is something that we often do in class, and we'll actually come up with lots of different ways to describe a bicycle, and people say, well, my bicycle is red. Well, my bicycle is blue. My bicycle's a mountain bike. My bicycle is a... Okay, so those are descriptive terms, but they don't really define the traits. And so that's the first thing we're going to do. The diagramming technique that I'm going to show you generally takes that as the starting point. So I'll tell you what it's called. It's called UML, which stands for Unified Modeling Language. Now, don't let that word language trip you up. It's not really a language the way Python is a language, or C# is a language, or Java is a language, or even as English is a language. It's really just a diagramming technique that we use. And I liken it to sheet music for programmers. If you hand a piece of sheet music to a competent musician, they ought to be able to play the song at least reasonably well as it's written down in the sheet music. Likewise, if you hand a competent programmer UML, they ought to be able to write at least a facsimile of the program that it describes without asking too many questions, at least getting the basic structure down. And of course, from there, we have to ask lots of other questions because that's what programmers do. They ask lots of questions. All right, so here we have our bicycle written up in a UML diagram. This is a UML class diagram. There are actually 14 different kinds of UML diagrams. This is just one of them, and it's probably the only one we're going to use in this course, just to annotate our classes so that we know what we're talking about. All right, so I have drawn a square, very simply, and put the word bicycle above it. So this is the basis for my class diagram. And then I've written down the traits that most people use to describe a bicycle. Now, I understand that there are more than this, and it isn't always necessary for you to model every single trait about a thing in the real world in order to make it into an object in your program. You really just need to deal with those attributes that you care about in your program. And in this case, I've picked 5 just as examples. And again, I'm sure you can think of more, but the ones that I came up with were color, make, model, usage, and number of gears. So color is fairly self-explanatory. Make is who made it. A lot of us have Schwinn bikes when we're kids. Trek bikes if we're really into nice bikes when we get older, or specialized, or I think I have a K2 bike. The people that make the skis, I have a K2 bike in my garage. It's a mountain bike. So that would be the make, and then just like cars, they have models. So I have a Trek X01, and the X01 is the model number. And then I thought of usage because I have 2 kinds of bikes in my garage. I have a mountain bike and I have a road bike. And so those are 2 different uses for a bicycle. But then I thought of all the other ways that you can use bicycles. You can use tricycles to haul things around. I know that's popular in Asia. And there are different uses for these bikes. Track bikes, for example, are used only to go very fast in circles. They don't even have brakes on them. So there are lots of different ways that bicycles are used. And then I thought of number of gears because when I was a kid, that really mattered. If you had a 10-speed bike, then you were a big kid. And if you had a 3-speed bike, then you were a little kid. So there are different numbers of gears involved. And now that I'm older, I know that there's a whole class of people who think that everything should be very simple and there shouldn't be gears at all. And so they only have 1 speed on their bike. So just different attributes for different bikes, different uses by different people. And this is what we're doing. We're modeling out a bicycle. So those are a few things that you can use to describe a bicycle. All right, so what I'm really doing here is I'm building something called a class, and this is the most fundamental topic in object-oriented programming. Classes. Essentially, a class is the code that you write as a programmer. Code. When I say code, I'm talking about a text file that contains all of the instructions that describe how your program works. That's basically the work product of a programmer. When a programmer goes to work, they produce code. And so we're producing code, and what we're actually making are class files. And you can think of a class as a blueprint for an object. So just the same way that you can use a blueprint to build a house or a building, you can use a class to build an object. So you can make lots of different objects from a single blueprint, and here I am getting muddy with the word object. You can make very many houses from the same blueprint. In fact, most housing areas, if you drive through them, really, housing developments, I guess I should say, only have 4 or 5 variations. All of the houses are essentially made from the same blueprint. And so you can drive around different areas. If you are in the DFW area, I used to live in a suburb called the Colony, and it was really evident there. I could drive down different neighborhoods and see the exact same house that I lived in. But there were differences, right? Obviously, the address was different, and that is an important analogy later on. But different things, there were different attributes on the house that were different. Some of them were painted different colors than mine. Some of them had upgraded their windows. Some of them had gotten new roofs, and so their roof was made of a completely different substrate than mine was. Maybe they had, better shingles, wooden shingles, and I had asphalt shingles. The point is that you can make lots of different copies of an object or a thing in the real world based on the blueprint, but they're not all the same, right? They're not identical to one another. And since they exist at different addresses, you can say that they are independent. They are not linked copies of one another. So if I change my door color, the person down the street 4 blocks over that has the house that was made from the same blueprint, it doesn't update his door color. It just updates mine. So those instances of objects out in the real world and in your program, for that matter, are all individual elements, and you can manipulate those things independent of one another. So a class, going back to this, is a blueprint. You make your objects out of classes, and then once you make your objects, then you can change things about them, and they're all individual instances of that class. So the first thing we do when we start making a class, and when we start defining one using our UML diagram, is that we go through and we basically just do the exercise that we just did. We come up with ways to describe our object, and we came up with traits. The real word for them isn't really traits, we call them properties. So we had a whole lecture on variables, and this is one of the things that changes when you move from procedural to object-oriented programming. Within the context of a class, a variable that's part of the class becomes a property, and so that's sort of attached to the class. In fact, we call properties by several different names. We call them properties, we call them, in a generic sense, we can call them fields, we can call them instance variables. Now there are some nitty-gritty details in the language that will make some of these things different. Like in C#, there's a difference between a field and a property. But at a high level, they pretty much do the same thing, so I'm sort of clumping them together for right now. So that first thing that we did was we made a bunch of properties, and that was what we put at the very top of our diagram. And then beneath that, we have methods. So it's one thing to describe, the traits, the physical attributes, the properties of something, but you also need to understand and model what that object can do. Things in the real world don't just sit there most of the time. I guess sometimes they do, but usually they do something. And so when you want to model what an object can do, then you're going to use a method. And going back to our earlier lectures, we had a whole lecture on functions. And functions moved into the context of an object just changed their name. They become methods. But other than that, they're the same thing. They have the same principal parts. They have the function name. They have the parenthesis. They have arguments. They have return types. Nothing changes except what they're called. So let's make a diagram with a few methods on it. And I just thought of some things that bicycles can do. They can roll, they can stop, and when I'm riding one, they sometimes crash. And I'm sure that we can come up with more than that, but this is just a small set of things that we can put in there. So at the top, we have all of our properties, and at the bottom, that's when we have all of the methods. So the top part is properties, the bottom part is methods. There's usually just a single line separating the two. I made it look a little nice by making them separate boxes, but you'll see it either way. You'll see it as separated or separated in some way, and it's usually just separated with a line. So the top is properties, and again, the bottom is going to be your methods. Now at this stage, I want to warn you of something that happens to programmers all the time, and that's something called analysis paralysis. And this is a term from the industry. What this means is, as you're going through making your UML diagram, it isn't really necessary, as I mentioned before, to go through and think of every single property that could potentially describe the object that you're trying to make. And it isn't necessary, as you start defining relationships between your objects, to try to think of every single interaction that could potentially happen in your program. If you do this, you're going to spend weeks or months trying to come up with the perfect UML diagram, and the perfect UML diagram probably doesn't exist, because if you get two programmers on a project, eventually they're going to disagree over how something should be implemented or how something should be diagrammed. So there is no perfect diagram, and so since there's no perfect diagram, then pursuing the perfect diagram is pretty much a fruitless exercise. One of the ways to get around analysis paralysis is to not try to come up with implementation details. And what does that mean? I've talked about, in different lectures, I've talked about things like variable types. There are integers and strings and booleans. Later on, you'll get into lists and different kinds of lists and collections and complicated objects and things like that that can be in your class. And it isn't necessary for you to come up with what all of those are going to be. So on our bicycle, we have basically a make and a model. Those are probably going to be strings, but I'm not going to put that on my diagram because I can figure that out when it's time to actually start writing the code. And it's usually a good idea to let the programmer do that. It isn't a foregone conclusion that you will be creating the UML diagram for your software. And so I think you would probably not appreciate somebody dictating what all of these things should be. Now, that I've seen people annotate in their UML diagrams what they think it should be. But I think at this stage, you should really treat our UML diagramming exercises like a brainstorming session or maybe an animator's storyboard. You're just trying to sort of hit this with broad strokes and come up with the ideas for the program rather than strictly how you're going to implement it. And I personally think the best thing to do when you're doing UML diagrams is to do them on a whiteboard or a piece of paper. If you try to start everything in a piece of software, what you're doing is you're conforming your thought patterns to the way the software works. And you may actually discount something as like, well, there's no good way, there's no button I can click that will do what I'm thinking right now. So I always encourage people to start off on a piece of paper or on a whiteboard, something along those lines. And then later on, it's fine to come back and transfer your diagram into some piece of software. There's plenty of diagramming tools out there on the market that you can buy, ranging from a few dollars to a few $1,000s, depending on what you're after in your diagramming technology. I personally like to use a program called Dia, spelled D-I-A. That's an open source program, and it's available on most platforms. And I'll probably be showing that to you in class at some point. But it's a very easy to use program. And the reason why you would want to do that is because I don't know about you, but when I draw on a piece of paper, it usually turns out being a napkin or the back of something, whatever I have handy. And your UML diagram will probably eventually become part of your project documentation. So you probably want to clean it up and make it nice and make it so that other people might be able to edit it, assuming they have the same software. And so it's good to have a soft copy of it. But I think that should come later after you've had your brainstorming session and you've started down the road of actually making progress on creating your application. Okay, so this is a point that I want to make at this stage since we're talking about analysis paralysis. And I'll give you the disclaimer, I am an unapologetic capitalist. I am in business to make money. I write software. That's how I make my living. And so I'm not one of these sort of open source people that thinks everything should be free. I'm not that guy. So with through that lens, let me lay this on you. It's the most important thing that a software developer or programmer, an engineer, whatever you want to call yourself, the most important thing that you can do is to ship software. Nobody ever makes money or makes progress, I guess you could say, if you want to be a little more delicate about it. You don't make anything designing software. You don't make money designing software. You don't make money writing software. That's an exercise in production. You don't make money testing. Shipping your software is how you measure your success. So you're not really a successful software engineer until you've actually shipped your product. Until then, it's just an idea, and it's just sitting on your computer, and no one can use it, no one can benefit from it, no one can gain from it. And so that's the most important thing. So you should try to do everything in your power to ship your software as quickly as you can. Now, you don't want to ship junk. You don't want to ship something that's untested or half thought out. But you do want to do just as much as you need to do to ship it and no more. And so that's another exercise probably for another day. But again, going back to analysis paralysis, you might be tempted to think that you have to get everything perfect in the planning phase of your project, and you don't. You'll actually do a lot better, and you'll ship your software sooner and faster and probably come up with a better product if you use a more iterative approach. If you do a few diagrams, write some code, see how it works, maybe spring it on a few potential users and see how they like it. And then you can adjust your UML diagrams, adjust your code, and adjust your process as you go, and you'll get a shipped product much faster that way. All right, so going back to sort of the more theoretical aspects of object-oriented programming, there are a couple of big, I call them big college words, that you need to learn when you're talking about object-oriented programming. And here are a few of them. The first three are actually defining traits of object-oriented programming. And then the last one is just something that happens a lot. It's a pattern that you should learn about early because you're going to be using it often. So the three traits that I'm talking about in this, again, this is sort of a basic intro. There are more traits than this, but the three that I think are the most important right off the bat are encapsulation, inheritance, and polymorphism. And then we're going to talk about composition as well. Again, that's just a pattern. It's not really a defining factor of OOP. So let's talk about the first one, encapsulation. And it's kind of a hard term to discuss. It really makes a lot of sense when you start doing it. But let's just assume that you got a brand new car. And to make my analogy work, I need to assume that you're not a mechanic and you're not one of these gearhead types that loves cars so much that you're going to buy a car based on what model has more torque than what other model. When you're really getting down into the nitty-gritty details, it sort of messes up my analogy. So if you're that guy or that girl, pretend you're not for just a moment, and let's think about cars the way most normal people think about cars. So when you get a new car, you are essentially a user of that car, just like somebody would be a user of your software. And there are a set of controls in your car that you really care about. You care about the steering wheel, the accelerator, the speedometer. You really care about the brakes. You care about the headlights. And most of us really care most about how good the stereo is. But you need all of those other things too. And you have a really strong vested interest in learning how these things work because many of them are safety features or features that you need in order to get your car to do what you need it to do, i.e. get you to work, get you to school, get you to whatever. So without those basic things, then it's really not all that useful. See, these are the most basic things that you can do with that car, and that's how you operate your car. So these are the things you need to know how to use. But beyond that, there are all kinds of complicated things that are going on inside your car that you really don't care about, especially newer models, anything made after, say, 1984, 85, is going to have a computer doing almost everything in it. Before that, it was very mechanical, and now it's very computerized, and that actually makes things a lot more complicated. Used to be we could pop the hood and fix most things with a set of wrenches, and now you have to have a diagnostic computer just to understand what's even happening or going wrong or going right in your car. So there's all this technology going on, and we don't need to know about any of it in order to use the car, in order to drive the car. So we don't care how the gearbox is controlled by the computer system unless, it's preventing us from going as fast as we would like. We don't care about the fuel mixture ratio, air to fuel mixture ratios happening in the engine. We don't care about spark plug timing, unless there's a problem. And when there's a problem, we by and large rely on our mechanics to fix that. So in our cases, there are all these things that we really care about in order to use the car, and then there are a whole bunch of things we really don't care about when we're using the car. In fact, we usually don't even think about them. And that's really a good example of encapsulation. So when you write software, you inevitably use classes and code and libraries and things that you didn't write. And this is especially true in C# because C# is not only a language, but it's also part of a framework. And a framework means that there are a whole bunch of tools and classes and things that are written within the language and sort of within the auspices of the language that you use that you don't have to write. So if you were a hardcore C programmer and you were not going to use any libraries but your own, then you would have to write things like, the ability to read a text file into memory, or the ability to write a text file to the disk. These are sort of excise tasks. This is something that you should not have to care about because those things have been around for so long, no one would understand why you were writing them from scratch unless you were on some sort of crazy new platform that didn't have them. So a framework really has all of that for you, but it's not just basic things, it's more complicated things too. So pretty much anything that you can think of, interacting with databases, interacting with the internet, dealing with large numbers, doing complicated math. In the case of Unity, we have a framework that lets us do a lot of things with 3D space that would require some really complicated math. And it's been reduced to a simple method call where you just supply some very simple parameters and it does all of the work for you. And this is really, again, the heart of encapsulation. You just want a few simple things to work with, and you'll let the guts of whatever code that you're using really handle all of the heavy lifting. Now, there are going to be times when you are the one writing the guts and doing the heavy lifting. And when you're doing that, in those cases, what you're going to do is you're going to use encapsulation to hide those guts and really just expose the parts of your class, the part of your code that we'll just say for the sake of argument, it's some other programmer that would need in order to use it. And so it's really just thinking about what you want to expose to a programmer, even if it's just you, and what you would not want to expose to a programmer. And so that's really the heart, again, of encapsulation. So there are a few things that come to mind when we start talking about encapsulation from a more programmatic point of view, a more of a programmer's point of view. And there are different things that you're going to hear. So you're probably going to go on to more classes in object-oriented programming, at least I hope you do. And you're going to hear information hiding is one of the ways that you can describe encapsulation. And that's not a bad boiled down phrase. We've sort of covered some of this. We've talked about how programmers create classes, and we want to expose those important elements that other programmers will use. And then if we think it's something that they're not going to use or they don't need to know, then that's when we hide things. That's where we're going to sort of protect the programmers that are using our classes from making really horrible mistakes that might cause their object to enter an invalid state. And we'll talk a lot about that throughout the course. So anything that you wouldn't want some other programmer to manipulate and worry about, those are the things that we're hiding. And we're not hiding because, we don't want them messing with it. You're not thinking about security in this sense. You're talking about ease of use and really sort of protecting programmers, even if that's just you, from getting your object into a state that would be bad or even harmful. And so here's an example. If you think about your speedometer, you don't have access to your speedometer in your car. So there's not some sort of wheel that some intelligent programmer thought, hey, I know this would be a great idea. I should be able to put some sort of knob or something so that I can override what you see on the speedometer with something else. That'd be great if you got pulled over, right? The cop says, how fast were you going? Well, you just click your little dial before he comes over and say, oh, I was totally going 25 miles an hour. And it says so right here on my speedometer. That's a bad thing if you think about it, right? Because now your car is not giving you accurate information. And it might even be possible with such a feature to make your speedometer say something that wouldn't make any sense at all. So maybe it registers a negative speed, or it registers something beyond the speed of light. Those would be two states that would be theoretically impossible. And so those are bad things in a programmer's world. An object in an invalid state is usually the cause of blue screens of death, program crashes, and things like that. So there are a lot of times with encapsulation when you're not just hiding something, you're also protecting your object from entering a state that would be really, really bad. So in this case, we would want to, as we're designing our speedometer class, make sure that the speed that comes off it is a read-only property and that you can't set it. So this is, again, a form of encapsulation, and you're preventing the end programmer, even if that's just you, from setting it to something that it shouldn't be, or setting it at all, really. It should only come from one place, and that's whatever mechanism is measuring the speed at which the car is traveling. All right, so this is something we've been talking about sort of between the lines, and I'll just make it really explicit now. One of your biggest jobs as a programmer is to never allow any object created from a class to enter an invalid state. And I referred to this just a minute ago. If you're creating a speedometer class, you don't want it to register something like a negative speed or faster than the speed of light or something like that. You certainly wouldn't want to do that on purpose, and you wouldn't want to do it sort of out of laziness. Well, I'm just going to make that a public property. Just expose it to the world and let them do whatever they want to with it. That is a bad idea. I'll give you an example from my own career. There was a bug. Now, this was completely unintentional, of course, but there was a bug in the V-22 simulator that we worked on, and it allowed the pilot to fly the aircraft upside down under certain conditions, which is, of course, not advisable or possible in an actual V-22 Osprey. If you don't know what that is, it's this tilt rotor helicopter that Bell makes. It's really popular with the Marine Corps, and it's also really popular in video games. I think I've seen more video games with V-22 Ospreys in it than I have actual Ospreys. So for whatever reason, game animators love these things, and that's what they are. So they're just helicopters, basically. And you really can't usually fly a helicopter upside down. That just doesn't work very well. All right, so if we had done a better job, we might have put better limits in there that prevented the pilots from flipping their aircraft upside down in the simulator, and thus maybe leading them to the conclusion that they might be able to do that in combat. That would be really cool and the basis for a few movies like Blue Thunder, but yeah, probably a bad idea in practice and in reality. So that's probably a really concrete example of making sure that your encapsulation is right, making sure that everything has a limit on it that needs to have one, and that those limits are enforcing, not allowing your objects to enter an invalid state. Okay, so big topic. I've talked a lot about it. I've probably talked it to death, but it's really, really important thing that you have to understand as you start making programs in C#. And you really can't get away from it, so it's another reason why we cover it so heavily. There are basically 4 words that you need to learn with respect to encapsulation and practice. And these are called access modifiers. I wish I had punched those letters up a little bit more in access modifiers. Maybe I'll go back and change them in post. But this is one of the most important terms, and you're going to see this term probably on at least 6 to 8 questions out of the 30 that are on your object-oriented programming test. So this is a really, really important topic, and I want to just sort of draw your attention to it more than I would anything else. So the 4 words that you need to learn: public, private, protected, and internal. And we really can't talk about the last 2 yet, but we can go ahead and start talking about public and private. So public, again, is an access modifier, and you'll see it. It's going to make a lot more sense when you actually see it used and when you're actually using it yourself. But for now, just realize that any object can reference a public property or method on another object. So you've got 2 objects in your program. One object can see the other object, but it can only see those elements that are marked as public. And then we have the opposite of that. We have private. So again, 2 objects sitting in the same program. Anything that's marked private would be completely invisible to the other object. It's only accessible to the class in which that code exists. And I know that's a little abstract, but I want you to sort of store that away for a minute and know that when we actually start writing this stuff, you're going to be using public and private and making the decision all the time, which one should it be? Should it be public? Should it be private? Or protected or internal? We'll talk about those a little bit later when we start talking about inheritance, but the first 2 are really basic. And those are the ones you use most often in Unity anyway. All right, so let's go back to our UML diagram for just a minute, and let's see how we integrate our public and our private notations into our UML diagram. So it's pretty easy. A plus sign means public, a minus sign means private. Doesn't get much more easy than that. So anything with a plus in front of it is telling you that you need to declare it as public. Anything with a minus sign in front of it, I made crash private because I guess I'm the only one that does that. But that's how it would look on a UML diagram. Okay, so moving on from encapsulation into the next big thing in object-oriented programming, and that is inheritance. So let's say that you make 2 classes that have some things in common. So let's start with two kinds of bikes, a mountain bike and a track bike. A track bike, if you've never heard of one of these things, there are these races that go on in these sort of circular tracks. I think they're called velodromes. And there's one in Frisco. If you're in the DFW area, you can actually go out there and ride your track bike on an actual velodrome. EDS made one, I guess probably back in the late 90s, early 2000s. And so it was sort of a big deal out there that they had these bike races. And it struck me as odd because there's some things that are different about track bikes. For example, they don't have brakes. In order to stop, you actually just, what they do is I think they just roll around and don't pedal anymore until they eventually just slow down. But they don't have brakes because, well, they're in a race, so why would you need brakes? And secondly, brakes add weight to the bike, even if it's a gram or two, and apparently a gram or two in the world of bicycle racing can mean the difference between winning and losing. So we have these two different things that are very different, a mountain bike and a track bike. A mountain bike is sort of like the Jeep version of any bike that you might own. You need to be able to go over to rocks. You need to be able to roll over branches and trees, and you need to be able to pop wheelies, they're called technicals. You need to do all these things in order to clear obstacles. So these are almost diametrically opposed, right? They're two vehicles that look alike because they have two wheels, handlebars, and a seat. But beyond that, they're used for two completely different things. Now, with that said, there are some things in common, right? So the mountain bike and the track bike have some things in common, but they also have some things that are not in common. So what you do when you start considering inheritance is you take those things that are in common and then you move them out into a different class. So what we can do is we can make something called a superclass, or a parent class if you prefer that term. And at this stage, then we have this bicycle class, and then we will say that the mountain bike and the track bike both inherit from the bicycle class. So what this means is when you use track bike, you'll still have color, make, model, and you'll have access to the roll method. Likewise, when you use the mountain bike class, you'll have access to color, make, model, and the roll method. But then you'll have all these magical superpowers that are unique to that particular object. So the track bike allows you to pedal backwards, and you'll actually go backwards because it only has, one. It doesn't have a transmission the way a mountain bike has, or a gear system, I should say. Mountain bike, on the other hand, if you've ever ridden one, unless it has coaster brakes, if you pedal backwards, nothing happens. So usually to stop, then you have some sort of disc brake system or a caliper brake system, depending on how much money you spent on your mountain bike. A really expensive one would have disc brake systems so that when you roll through the mud, your stopping power is not limited by a wheel rim, which is probably now slippery or dirty. All right, so again, this is just bicycle as the superclass, parent class, and then mountain bike and track bike are inheriting from it. The key phrase to remember when you're thinking about inheritance is the phrase is a. So how do you apply this? Mountain bike is a bicycle. A track bike is a bicycle. And you'll note that we have these two broad-headed arrows drawn pointing downwards. And that is how we symbolize inheritance in... I just realized these are backwards. The arrow should actually be pointing at bicycle, not track bike. I'll fix that in the slides later on. All right, so just follow the arrows, and that should point to the superclass. And that's how you consider the is a relationship. So that's is a bicycle, or mountain bike is a bicycle, track bike is a bicycle. And there's another key phrase when we talk about composition, has a. So you have to remember the difference between is a and has a. And we'll talk about has a little bit later. And again, just to sum it up, mountain bike is a bicycle, track bike is a bicycle. And that broad-headed arrow is a. Okay, just a couple of inheritance odds and ends need to be covered. And C# and Java are very similar, so I'll kind of talk about both of them because I know a lot of my students have taken a Java class. Sometimes you're even taking a Java class concurrently with this one. And so we'll talk about sealing a class. When you seal a class, this is what a programmer does when he wants to make sure that no one can inherit from this particular class. So if you don't want a programmer to extend your class, you basically want to stop the inheritance chain. What you do is you just make your class sealed, And there's a keyword for that, and it's just sealed. So I'll show you how to mark something sealed in one of the labs, but it just goes up as part of your class definition. So if you're taking Java, it doesn't say sealed in Java, it says final. So that's how you stop someone from inheriting, or another class from inheriting. I shouldn't say stop someone because that makes it sound like it's a security issue, and it's not. That's how you prevent a class from being subclassed. And then you can go sort of the other polar opposite, and you can deal with something called an abstract class. An abstract class can't be used directly. It has to be subclassed in order to be used. So basically, it has to have child classes. And there's a keyword for that one too, and it's abstract. I'll show you a usage of that when we get into our diagramming exercise, which apparently it's time for now. So we're going to do a Dungeons & Dragons character OOP lab assignment, and that'll be in a different video. So that is the first part of object-oriented programming. We'll do this lab, we'll do some practical things, and sort of cement these basic ideas that I've presented, and then we'll pick up with object-oriented programming part 2, which will be a much shorter lecture because we've covered most of it already. We've probably covered 2/3 of what I want to cover in just this part. So let's go off and do our Dungeons & Dragons modeling exercise, and then we'll write some code, and then we'll come back and talk a little bit more about object-oriented programming.